Can you hear me?
Yeah, cool. Then yeah, I will introduce you first, and then you can go ahead and have your presentation. So Professor Fernandes is an assistant professor at the University of Wisconsin-Madison in the CS department. His goal is to enable society to gain the benefits of emerging technologies without the security and privacy risks. Professor Earlence Fernandes has received 2 Best Paper Awards at IEEE SMP and IEEE Secure Development for his work in smart home security. He will give his talk today about physical attacks on object detectors. And let's welcome him.
Well, thank you. Thank you for the introduction. Thank you for the opportunity to speak today. I appreciate it a lot. And I also appreciate the effort that goes into organizing these virtual events at a time like this. So yeah, I'm a professor in the CS department at Wisconsin-Madison. I do research in system security, kind of broadly defined, and one of my focus areas nowadays is cyber physical systems. So, unlike many of the speakers, at this conference, this workshop, I'm not a computer vision or even a machine learning researcher. And so, much of the things I'm going to say today kind of come from kind of a computer security perspective and how, some parts of the computer security community view some of these adversarial example problems. Okay, so, as we all know now, these adversarial examples are a major research area, a lot of papers being written, and early adversarial examples kind of introduce this notion of digital attacks, right? So the attack is going to basically digitally add and subtract pixel values to an image, and then these changes are going to be so small that a human is not going to be able to see it. And then what you end up with is, for example, in this classification task, this dog may look like something that is not a dog to the classifier, right? More recent work kind of introduced the notion of physical adversarial examples. And a lot of this early work was kind of done in the context of classifiers. And so here I'm showing you an example of our prior work that appeared at CVPR some years ago. And here the idea is that the attacker can somehow manipulate a physical object. In this case, in our case, we were interested in stickers on stop signs. And the result is that once you run an algorithm to compute these kinds of adversarial examples, you can modify a physical object, and then you can take an image of that object, and then that resulting image will be misclassified. Now, of course, our work was not the only in that space. At around that time of that work, there was a lot of concurrent efforts, and we have seen many examples. For example, people can wear different kinds of eyeglasses. You can print things on papers that can hijack the attention of these classifiers, and so on and so forth. And the common kind of thread in all of this work was that it focused on classifier networks, right? And so that is all well and good, but a more fundamental question kind of coming from the computer security world is that, why should we care about these kinds of attacks? And more specifically, why should we care about these physical attacks, right? Well, should we care about them at all? And one of the driving questions in our work, and I presume in a lot of the concurrent work at the time, is that, we are seeing many of these machine learning models being used in these cyber physical systems like cars and voice assistants and drones and stuff like that. And we find that they're being used in pretty critical aspects, right? So, I mean, you can see that in the cars, for example, they use it in perception and sensing, and sometimes even control. And so naturally, the implication is that, if somehow these adversarial examples are physical and they can cause behavioral changes in these physical systems, then that would be very bad for their safety and security. Okay, but that's not the complete answer why we should care about these physical attacks. The second part to that is kind of the threat model, right? So as I mentioned, a lot of the early work had this digital threat model where you would manipulate the pixels of a file that goes into the machine learning model. But again, if you take this in the context of cyber physical systems, this kind of threat model is not the most reasonable, because if you assume that an attacker somehow can digitally manipulate the pixels of an input vector going into a model running on a vehicle, they have already won. Right? They've already won the game. We don't need to, there are easier ways to carry out the attack. They have digital access to the computer systems on these things. And so, the second part to answering this question is we should be concerned about this is that only if these adversarial examples will have macro level effects. Okay, and I put a double star here because, from a cyber physical systems perspective, machine learning is not the first vulnerability we have ever thought about for these systems. In the computer security world and the CPS world, we have many other kinds of vulnerabilities that do have end-to-end effects that we have looked at before. But the new thing is that, if these machine learning attacks can have an end-to-end effect, then it becomes yet another attack vector that we have to take into account in our threat model as defenders when we are trying to design robust physical systems. So all of the work in understanding these physical attacks, I view it as kind of taking a first step towards this larger question of whether we should care about these adversarial example or physical machine learning attacks at all. And so, my talk today is kind of going to be in three parts. First, I will discuss some early work we did some years ago that kind of takes another step in this direction of answering whether we should care about physical adversarial examples. And so, I'll talk about this paper we published at Boot. So, for those of you not from the security community, this is the Usenix workshop on offensive technologies Boot. It is a place that is exclusively publishing attacks on various kinds of cool attacks on systems. So I highly encourage you to check that out if you're interested in what's going on. Then I will briefly review some concurrent efforts that attack these object detectors in various ways. And finally, I will take one step back and try to again contextualize all of this work to show you where we are and where we must go, kind of again in service of answering this larger question of whether we should care about these kinds of attacks or not. Okay, so we have seen this work in the context of classification. Now, in the deep learning world, in computer vision world, we have many kinds of tasks. Object detection answers the question where the objects are in the scene and what are they as well. So it's like classify, detect and classify. And one step further is semantic segmentation, where almost every pixel is kind of being labeled as part of some larger concept. For example, building window skies and all of that. The focus of our work was on these object detection models, and that's kind of what I'm going to dive into here. Before I dive into that, I just want to spend a few minutes motivating why object detectors in particular, right? Why am I not focusing on other things? Obviously one reason is that they detect and classify. So in some sense, they are more useful and more general than a classifier. More useful to CPSs is that they work at relatively high frequencies, right? So that is like they can process and give you output at high frames per second. And this is very useful for real-time systems. So all of these cyber physical things operate in real time, and your machine learning somehow has to be able to operate in that kind of constrained environment. And finally, we are beginning to see some of these object detectors being used in realistic systems. So for example, Apollo Auto is an open source self-driving car software from Baidu. And I will kind of get into some details of this towards the end of the talk. So, unlike classifiers, there are a few kind of specificities in object detectors that make it a little more challenging to attack than the work we did with classifiers. And so here I've kind of listed a few of these examples. The first is that, a detector kind of processes an entire scene. And this kind of implies that they have a lot of contextual information to take into account while they're making that prediction. Second is that, the model is not constrained to, kind of do or die, like give me a label or else, you just die. Here they can produce many objects, many labels, so they're not constrained in that kind of, that setting. Third, and this is kind of the most interesting one, the location of my target object, right? So as an attacker, I have some target object that I want to attack. the location of that target object within the scene can vary widely, right? Unlike in a classifier, which, where the images are relatively tightly cropped to the dominant object, in a detector, these objects can be anywhere. And so, at the time we were doing this work, we had just completed the project on the stop signs and classifiers, and we were curious, whether it is possible to extend that framework that we had built and see if we can make small changes to it and still attack detectors. And that was kind of, one of the questions we were trying to answer. So before I go into, how we ended up attacking those systems, the object detectors, I'll give you a bit of a review on the algorithms we use to attack classifiers, because the detector algorithm is a very small variation on the classifier attack algorithm. And so, in classic adversarial example style, you want to minimize some kind of distance function between two, say, images here, x plus delta and x. And delta is your kind of attack, your adversarial perturbation, as long as that perturbation causes the classification label to change. And we don't really work with this formulation. We use kind of a relaxed formulation. This is pretty standard, and we use kind of a loss function to kind of approximate the distance between the output of the classifier and the attacker label. Okay, and this is a pretty standard formulation. And one of the big things in these physical attacks, independently of classifiers or detectors, one of the challenges is to make them robust to changing environmental conditions. And so one of the primary ideas in the work was to essentially, when you're training the attack, you want to model ahead of time the effects of the environment on the perturbation delta here, right? And the idea was to basically optimize over a set of images such that in expectation, your adversarial perturbation is going to gain robustness to those chosen features through those chosen images. And there are multiple ways to kind of sample from this distribution. We ended up doing a combination of taking actual real images in the real world that simulated these environmental conditions and synthetic transformations as well. And I guess, a point of difference between the ICML work of Atelier et al. is that they used synthetic transformations. So that kind of will give you, a robustness to environmental transformations. And notice that this is a framework, right? I can keep adding different kinds of transformations if I want robustness to those conditions. And that is really the key point that will be useful in attacking detectors that I'll show you in a couple slides. Another thing about these physical attacks is that we can't just add noise everywhere, right? So unlike a digital attack, in the physical world, everywhere literally means everywhere. And so we need to make it a little more well-defined. And so we introduced this notion of a mask. You can think of it as a matrix with ones and zeros, and so we simply do an element-wise product with the attacker's kind of delta, the attacker's noise. And of course, depending on the shape of the masks, you get different kinds of attacks. And I've kind of shown you very simple black and white sticker attack here. Choosing a mask is a bit of a question. I would say it's still an open question. And we basically came up with a very simple hypothesis that we can use an L1. We can do 2 rounds of optimization in L1. L1 is a sparsity norm, and the idea is that if the optimizer will basically favor less pixel changes over many pixel changes, and they will kind of coalesce around important parts of the object. And so we kind of did this process, this multi-round technique, and we kind of produced these stickers here in a manual process, right? So we look, as humans, we look at the output of L1, and then we say, okay, maybe we should put a sticker here or somewhere here, and that's how we construct the mask. This, of course, is an open question. How do I jointly optimize the attack and the mask? Anyway, so, at the end of all of this, you run all of this, you kind of get these sticker attacks, and we did a bunch of experiments in the lab and in the physical world, and we find that they work. Okay. So that was the review. Now, it turns out attacking object detectors, at least in the context of these traffic signs, is not very different. As I alluded to earlier, one major change from classifiers is that the target object can appear anywhere in the scene. Right? And so in a sense, you want your adversarial perturbation to be effective at many of these locations within the scene. And so, put another way, you want translational invariance, right? You do not want where the object is to affect kind of the quality of the attack. And so conveniently, this framework, basically will allow us to model this translational invariance as yet another transformation. So essentially what we do is we model a fixed set of positions within the scene for a target object. We move that object between all of these positions, and then we optimize that over those set of generated images. And so the idea is that if you do this enough times, in expectation, whatever perturbation you calculate will be invariant to where it is located in the scene. Okay, so that was the first realization when attacking object detectors. The second realization was that the loss function is going to be a bit different. So unlike a classifier, where you have some kind of cross entropy loss, you have a fixed, probability distribution that is being output. The output of an object detector is a little more complicated than that. And so, here what I'm showing you is kind of the YOLO V2 output format and how we adapted the loss function to work there. So at a high level, essentially YOLO divides a scene into S by S cells. In the implementation we experimented with, S was 19, so this would be 19 by 19. Each grid cell is responsible for kind of predicting up to 5 bounding boxes. So this is kind of a parameter of how the network is configured. And each bounding box is technically these two vectors here. One is kind of an objectness vector, which simply says, okay, what is the probability that there is an object in this grid? And of course, where is it? Center and of course width and height. And then there's a full probability distribution that basically says, what this object might be, right? So if you put all of this together, the output of the YOLO model is actually a 19 by 19 by 425 tensor. Okay, so this is very different from your classifier style output, and so your loss function needs some thinking. Right? And so one of the goals in this attack, in this proof of concept, was to simply, make the stop sign disappear, make the target object disappear. Right? And so we designed a loss function to kind of encode that idea. And so essentially the idea, I've shown it to you here. I've taken this from the paper, but kind of the English description is that, at any round of optimization, you look at the output, you find the kind of the maximum probability stop sign, right? Out of all the predictions, what's the stop sign? Which object is the stop sign and what's the maximum one? And you minimize that directly. And you keep doing this through several rounds of optimization, and eventually the probability of a stop sign appearing in the scene will be below kind of the notification threshold of YOLO. So I believe YOLO uses a certain threshold, I believe 20% in our implementation. If the probability of an object is above 20%, it is going to show you that information saying that, hey, here is this stop sign. If it is below that, it's going to suppress. Right? And so the goal of the optimization was to essentially always minimize the probability of the stop sign. Okay, and like the classifier work, we did 2 styles of attack. We did an attack on with a poster, so like the entire object is covered with this big poster, and we did, of course, stickers where we again manually chose a mask. Similar to prior work, we also did this similar kind of evaluation where we record a video of a camera moving towards the stop sign, and then we simply sample video frames and count the number of frames in which the stop sign was not detected. Right? In this paper, we did kind of two styles of attacks. We did white box attack, we did black box attack, and different settings. Okay. Across the board, I mean, I would argue that, you know, for a first attempt at attacking object detectors, the performance was pretty reasonable. For most part, you know, this the stop sign is kind of disappeared from the output of the model. Okay, so here is kind of a quick video of a poster attack on YOLO V2. You know, clearly, for some reason, it somehow notices the person, but the kind of the very obvious stop sign is not detected. Instead, there's like refrigerator, banana, umbrella, all kinds of strange things. Here is the same attack, but on a real object with stickers on top of it. Now it's looking, it's noticing bottles again instead of the very obvious stop sign. We also tried this kind of this black box transferability. So faster RCNN is another state-of-the-art object detector system. And you know, this is black box in the sense that we just train it on YOLO and just run it on our faster RCNN, see what happens. For most part, it works okay, but you know, we didn't try to do any special kind of transferability enhancing techniques. Another kind of attack we tried during this work was to kind of create objects out of nothing, right? So we want to kind of cause the detector to hallucinate the presence of objects that humans would disregard as meaningless, right? So for example, this thing I've shown you here, if you print this out on a piece of paper, YOLO would recognize it as a stop sign when, you know, to a human being, at least to me, it looks like a heart of some type. There again, you know, you have to kind of think of a specific loss function. So here, you know, because of the way YOLO works, recall that there is this objectness score and then a classification score. We kind of did this optimization that has two components to it. First, we want to get the model to recognize that there is an object in there, right? So I'm setting it to 0.2 or 20%. So this will at least, you know, show up or kind of get YOLO's attention as, hey, you know, there is an object there. You know, this is interesting. We should probably classify it. And then once we hit that threshold, we switch and we start optimizing the presence of a specific class. So in this case, you know, I wanted a stop sign. And so basically we say, okay, now that there is an object, we need to make it look like a stop sign to this model. So this is kind of a creation attack, attacker loss function. So that is the extent of what we did in that paper. At around that time, again, you know, this is an active area, a lot of concurrent work, a lot of follow-up work. There's another attack called Shapeshifter that did similar styles of attacks on faster RCNN. Right? So we did YOLO V2, this paper did faster RCNN, and you know, you kind of have similar results on these detectors. Of course, there is even more recent work. So for example, there's this interesting paper where you can like print a t-shirt with some weird patterns, and then that somehow makes you invisible to face recognition systems. There's also, I think, believe at this CVPR, these universal physical camo attacks, you know, that will make you look like some other kind of class. So there's a lot of interest in this area, a lot of concurrent work, a lot of follow-up work. And now for this final part of the talk, I want to take a step back and kind of contextualize some of the research we have done and some of the research this community is doing and what we have seen so far. And so, you know, recall from the first part, I said that, you know, one reason for caring about physical attacks is that, you know, if they have macro level effects on physical systems, then it'll be a problem. And so let's look at one system. So this is Apollo. It's a self-driving car system. It's open source. And this is kind of their perception pipeline, right? So They have various kinds of sensors. They have cameras, LiDARs, radars, all of that. And then they go through several rounds of processing. Right? There is traffic light detection, object detection, lane flow detection, many, many things. There's all kinds of tracking algorithms, sensor fusion, many things going on. We are right here, right? So we are kind of like what we have shown so far is kind of physical attacks on object detectors, right? So this is one component of the pipeline. We can trick this, but that's where we are. Now, I guess it is obvious, hopefully it's obvious to you here that, we are after end-to-end attacks, right? My claim is that we only care about physical examples in these kinds of systems if there is some kind of end-to-end effect on this entire system. In terms of physical level attacks, this is where we are, Now, of course, I again caveat this with double stars, because in recent times, there has been progress. There has been progress in kind of understanding, if we had to take things some more steps further, what that might look like. So there is some work at ICLR that essentially looks at this tracking process that runs Kalman filters to kind of make predictions one time step into the future about various kinds of objects self-driving car is seeing, and what you might do to fool that. Of course, this work is still in the digital space, and they use only camera data, but as real systems, they kind of do sensor fusion as well. So it is a step in the right direction. However, we still need to understand whether these attacks really have that end-to-end effect in the physical world. All the work I've shown you so far is kind of on these relatively two-dimensional objects, rigid objects. There's work on attacking different kinds of sensors like LiDAR as well. But again, the same kind of point remains. We still do not have an understanding of, if I want to create an end-to-end effect as an attacker, how am I going to go about doing that? Okay, so I'd like to end with a few points and some open questions that I do not know the answer to, and I'm happy to discuss them further. So the two kind of learnings I take from all this work is that we can attack classifiers and object detectors physically. We still need to understand physical macro level effects, and there is work kind of going in the right direction, kind of going in that direction of understanding how we might cause these macro level effects with these attacker algorithms. The one big thought I'd like to end is kind of along this theme of threat modeling. So, as computer security researchers, this is a very basic thing we do, often at the start of a project, right? It's a very basic activity, and it's something that really keeps me up whenever I think about autonomous vehicle security. And I'm going to contend that we still don't have a reasonable threat model for end-to-end physical attacks. So for example, where in the physical world is the attacker? Are they on the side of the road? Are they somewhere above the horizon of the vehicle, above the road? Are they a human being, a pedestrian? Are they another vehicle? If an attacker is modifying some vehicle, will the owner of that vehicle notice? What do they know about the system under attack? Right? So if you're Tesla, you're not going to give out your machine learning models. Maybe you'll give out hard labels. How do we create those physical attacks with different kinds of assumptions about the system under attack? And of course, what can they modify in the physical world without arousing suspicion among many observers? So, with that, I'd like to end. Thank you so much for the attention. As I mentioned in the start, we are a newly formed security group, MAD-S&P. It stands for Madison Security and Privacy. If you're interested in doing this kind of security-oriented work for adversarial examples, we are looking for students. We're looking for postdocs. So thank you again. I'd like to acknowledge my collaborators. A lot of this work was done with a lot of really great people, and thank you for your time.
Yeah, thanks a lot for your great talk.
Okay, so I will mute myself.